Today we're going to have like 2-hour review session for solid mechanics and foundation in the FE exam. I guess all of you can say that 2 hours is not enough to cover everything. But what I want to do first to go over some basic definitions, some principles in solid mechanics, and then I'm going to solve some example problems. And also you're welcome to ask any specific question, or if you want me to solve any type of problem, we can go over that problem too. So some just information about the exam. You know that the FE exam has 2 sessions, morning session and afternoon session. In the morning session you will have 120 questions in 12 different topics. There are pretty much generic, like mathematics, like chemistry or computers, or those kind of general topics. The afternoon session, which is more technical or civil oriented, you will have 60 questions in 9 different topics. And you see the contribution of each topic in the afternoon session. You see that for solid mechanics and foundation, you will have 15% of total percentage for this part of your exam. So it's important to basically try to answer solid mechanics and foundation question. Some general tips, very useful. I use those tips for myself, and I think they're very useful. First, calculator. I've seen several people burn because of just the calculator. Make sure that you have the right calculator. They're very tough in terms of calculator. If you have even a one letter, if they say, for example, is the model TX, is you have to have the TX. If you have TX1, they don't let you to get in the exam. So make sure that you have the right calculator. The second thing is work quickly. It's a matter of time. You have to keep track of your time. In most cases, I would say over 90%, the questions are not difficult. It's how you manage your time. You have to make sure that you're on time. I think the key tip is to review the FE manual before the exam several times. When I say review the FE manual, I mean to know which page or which section you can find, for example, material related to, for example, solid mechanics or foundation. Because in most cases, it's a matter of finding the keyword, the right keyword. If you find the right keyword, it's very easy. Just you can easily find the equation, and you can plug in number and find the answer. So it's very important to review the FE manual and know about different section of that. And sometimes they have some tricky question. Read the question and also the answer the choices very carefully. Use all the time that you have. Don't waste any time. You just sit to the end of the exam. And some other minor thing like your ID or paperwork, and also have a jacket sometimes. It's cold in the exam, and it's good to have a jacket. And also your lunch. So it's a long exam and you have to be prepared for the afternoon, so have your lunch ready. Okay, for solid mechanics and foundation, what are we looking at? For the solid mechanics and foundation, you see different topics. There are mostly from solid mechanics, but we teach in solid mechanics. I see a few students sitting in my solid mechanics class, like starting from index properties and solid classification, then phase relationship, something related to lab and field test, effective stress, retaining walls. Usually we cover retaining walls in the foundations class. How many of you have had the foundation class? So almost everybody had. Did you have the retaining wall section in the foundation class? Like lateral earth pressure, retaining walls?
Yeah,
It's just that little bit.
Oh, you are still the same people? Oh, sorry. So why are you here again? So you didn't take the exam last year? No?
We have to wait for a graduation semester.
Okay. Okay, I'm going to give the same lecture if you want about retaining wall or lateral earth pressure. Bearing capacity in your foundation class, different foundation types, again for foundation class, consolidation and differential settlements. We have slow stability. I'll be teaching slow stability this semester in solid mechanics. And I think last year we had the same issue, and we just had a quick review of slow stability, didn't we? For foundations? I think for slow stability. Did you have anything in your foundation class?
Not as hard as that.
Okay. Okay, and also for solar stabilization. Some of you already seen those slides. Just quickly go over that, and I think it will be more useful to solve some example problems. First, starting with index properties, of course, the first thing that you need to know is how to use particle size distribution. We use particle size distribution to characterize coarse grain material. Coarse grain material means sand and gravel. And what's the boundary between coarse grain and fine grain material? April?
Number 8.
April?
Fine.
It's number 4.
Coarse grain and fine grain. Sieve number 200. The boundary, remember that sieve number 200 is the boundary between coarse grain and fine grain material. Anything passing from sieve number 200 is fine grain. Anything retained on sieve number 200 is coarse grain. The first thing that you have to look in any particle size distribution result is to look at the passing number 200. It's the key. Just looking at passing number 200, you can say either it's coarse grain or fine grain. And sieve analysis is we will have a stack of sieves, and we will wash out fines, and then we shake the stack, basically. Then we weigh sieves and plot fine versus grain sizes. So remember that we use sieve analysis to characterize grain size, or the coarse part of ore soil. The first thing that you need to look at the percentage passing from sieve number 200. We had this discussion this morning, not this morning, I guess Monday. We have two classification systems that we mostly deal with. First one is Ashton classification system, which you see mostly in highway type of project. And the second one is unified soil classification system, USCS. USCS classification system, we have ASTM standard for that, and I would say is the most commonly used classification system. We will discuss about soil classification system. You usually have at least, I think, 1 or 2 problems from soil classification. So it's easy, it's just a matter of using your chart. How do you use the table and chart? If we go to FE manual, where is that? Let's go to page 137. 7, yeah, same thing. All of you should have this. Everybody has the manual. Does everybody have the manual? Do you have the manual? Okay, this is the the table that you have to use for soil classification system. Whenever you want to use a soil classification system table, you have to start from left. The first thing that you have to do, I don't know if you can read or not, starting from left, if you see here, here it says that coarse grain soil, fine grain soil. So you have to start from left. First, you have to see how much fine do you have. How can we say that? Based on percentage. If you have less than 50% passing from sieve number 200, you have to just work on the top part of table. So the first thing, sieve number 200. If you have more than 50% passing from sieve number 200, you have to work with just the bottom part of the table. This is unified soil classification system. We have a different classification system, which is AASHTO classification. Instead of 50%, AASHTO uses 35%. So it's just remember the difference between AASHTO and USDS classification system. In most cases, you need to use the USDS classification system, unified classification system. So for the unified, it's just half. If you have less than half or more than half. So the first step is to see if it's fine grain or coarse grain. And then, for example, if it's coarse grain, so I'm going to write it down, for example, for USCS. Start from left. Okay. Percent passing percent passing from sieve number 200. If passing is greater than 50%, is fine. If it's less than 50%, is coarse. It means that you have the first thing that you have to look. Now let's assume that you look at passing sieve number 200, and we can say it's coarse grain. If coarse, now you need to see how much sand do you have and how much gravel, because when we are talking about coarse grain material, we are talking about sand and gravel. In USCS classification system, the upper boundary or the largest particle size for sand is anything passing from sieve number 4. So if it's coarse, you have to find out sand fraction. Sand fraction is anything passing from sieve number 4 and retained on sieve number 200. So it gives you the sand fraction. So the first thing that you need to do is, first, coarse or fine. Second, if it's coarse, how much sand, how much gravel. To find out sand fraction, to figure out how much sand do we have, you can say, for example, percent passing from 200 is if, for example, if passing from 200 is like 15%, and passing from 4 is 55%, how much sand do we have? We know that we have 15% fine. What does it mean? We have 15% fine. It means that we have 85% coarse. The soil is either fine or coarse. Okay. We have 15% passing sieve number 200. It means that we have 85% coarse. Within that 85% coarse, we have to see how much sand do we have. Now, to find out the sand fraction, we have to subtract passing. It gives you sand percentage. Okay. Then it means that how much gravel do we have? 15. Why? How much fine did we have? 15. How much sand? 40. 55. 45, around 100%, yeah. It means that gravel is 45%, just for this example. But in general, gravel can be found by 100 minus percentage passing from sieve number 4. It means anything retained on sieve number 4 is gravel. Okay, so we already found the fine content. In USDS classification system, we have fine, sand, and gravel. To characterize the fine portion, we cannot just use sieve analysis. We need to use another test, which is error limit test. So remember that sieve analysis just can tell us we have how much sand, how much gravel, and how much fine. The fine portion includes clay and silt. But we have to use error test result to figure out the portion of sand and the portion of clay for the fine content. All we can say from sieve analysis is how much sand do we have, which was passing from 4 minus passing from 200. It gives you the percentage of sand. And for gravel, retaining on anything retained on sieve number 4 is gravel. So, for example, for this sample, for this example, we have 15% fine. How much sand? 40% sand. How much gravel? 45. First, we can say that it's a coarse grain soil because we have 85% coarse grain. Within that 85%, which one is bigger? Which portion is bigger? Gravel or sand? Gravel. So mostly we deal with a gravelly soil. Now, the second column, the next column here, it says that if it's coarse grain, I guess it's better. Now, we are done with the first column. The second column says that gravels, more than half of the coarse fraction, is larger than sieve number 4. It means that more than half of the coarse grain fraction, just the coarse grain fraction, which was how much here? 85%. So you have to look at just the coarse fraction, and then you can say if it's gravel or sand. Now you can say it's gravel. So we are done with the second column. Third column, we have to see how much fine do we have. The third column asks us how much fine do you have. How much fine do we have here? 15%. Remember, if you have fines less than 5%, you can simply ignore it and say that it's very low. If you want to quantify the term very low fine content, is anything below 5%. If it's less than 5%, you don't need to be worried about it. Then we call clean sand or clean gravel. Clean sand means we have very low fine content. But if you have fine contents more than 12%, you have to check the properties of the fine portion too. So you have to add a symbol for that fine portion. So less than 5%, above 12%. Anything between these two values, between 5 to 12%, is called borderline soils. For those borderline soils, we have to use dual symbols. For other soils, we have, in USDS classification, we have a group symbol and we have a group name, yeah? Group symbols has 2 letters. the first letter is the main type of soil. We have S stands for sand, G stands for gravel, C stands for clay, and M stands for silt. But we may have other letters too that we need to use for group symbols. For the group symbol, for the second letter is somehow explained about the properties of that soil. For example, we have W for the second letter, this first letter. Second is W stands for well graded. P stands for poorly graded. Those two letters, we use those when we have clean sand or clean gravel. We don't need to be worried about the fine content. We can just classify our soil based on the coarse portion of our soil. So when we say well graded or poorly graded, what does it mean? Does anyone remember? How can we say?
Variety of grain size. And poorly is one
size.
size.
Those well graded or poorly graded, you can find out about those terms based on particle size distribution. If you remember, we calculate two coefficients, C sub C and C sub U. We will see those on the slide. And also, let me write the other parameter, the other second letters, and then we'll get back to that. Other second letter that, remember, you can add those second letters just for coarse grain. Then you have fine content less than 5%. But sometimes you have to use other second letter, especially for fine grain coarse, fine grain soil. H stands for high plasticity. And L stands for low plasticity. Plasticity is a parameter that we care about that just for fine grain soil. We don't have such term for coarse grain material. When you want to classify a clay or silt, you have to somehow tell me how much plasticity you have. So we use those terms too. So for USGS classification, we have a group symbol which has two letters. Okay, the first letter tells me the major portion of our soil sample. The second letter tells us more about type of soil, particle size distribution, shape of particle size distribution, because those parameters, those well graded or poorly graded, are based on C sub C or C sub U. C sub C is curvature coefficient, or C sub U is uniformity coefficient. It shows us how wide is the particle size distribution. If the particle size distribution is narrow, we call the soil poorly graded soil, because we want our particle size distribution to cover a wide range. And we have some criteria for C sub C and C sub U. If, for example, C sub C is between 1 to 3, or C sub U is greater than 6, we call it well graded or poorly graded. You have those numbers in that chart. But remember, those two letters are used just by coarse grain material, and when you have fine content less than 5%. Those two second letters, H and L, are used by fine grain soils like clay or silt to explain plasticity. So the first thing that you need to do is to use sieve analysis. And you can see this is typical Stevenson particle size distribution. Basically, you plot percent finer body weight to grain size, and you can see different groups by unified classification system. As you can see, in most cases, we call anything between sieve number 4 to sieve number 200 sand. Anything below that is fine, which includes silt and clay. Above sieve number 4 is called gravel. Okay, we said that we need to calculate two coefficients to characterize the coarse grain part of our soil. The coarse grain part of our soil, we calculate C sub U uniformity coefficient or C sub C curvature coefficients. It's D60 divided by D10, D squared 30 to D10 to D60. When we say D10, what does it mean? D10 means?
Under which 2%?
10%, the particle size that you have, 10% passing from that particle size. So you can, for example, look at here, just for example, for D10 or D30, you can draw a straight line from 30%, intersect the particle size distribution, and find the corresponding grain size on the x-axis, and it's your D30. And for the fine grain part, we cannot use sieve analysis. We use hydrometer hydrometer test. It's basically it's a different test. We use that to find. It's also called sedimentation test. It's basically the velocity. It's based on the velocity that particles settle down, and based on that, you can find particle size. We use hydrometer analysis to find particle size distribution for the fine portion of our soil. But remember, particle size distribution is not enough to characterize a soil behavior, especially when you have fine grain soil. For fine grain soil, means clay and silt, you have to know also about the plasticity of soil. And those are aerobic limit. We have some liquid limit, plastic limit, and also shrinkage limit. Basically, those limits are moisture contents that transfer the soil mass from one phase to another phase. For example, when we say liquid limit, it's the moisture content that it transfers the soil from semi-solid phase to liquid phase. No, sorry, from liquid limit is from plastic phase to liquid phase. It's like this. Let's read. Those limits are moisture content, and it's basically to see if you assume you have, if this is moisture content, for fine grain soil, if you add more water, you start to show some sort of plastic behavior. So it depends how much water you add, you may have different phases. If your soil is very dry, you have just solid particles in your soil, you are in solid phase. If you keep adding water, it will move from solid phase to semi-solid. You will get some more water between those solid particles that kind of lubricate, soil particles that can move on each other. If you keep still adding more water, it will it will transfer the soil mass from semi-solid to some sort of like plastic material. Now you see more plasticity. But if you keep adding water, it will become like a liquid. Okay. The moisture contents corresponding to each boundary called aerobic limit. For example, from solid phase to semi-solid phase, we called it shrinkage limit. What does it mean? The shrinkage limit means that it's the moisture content that below that, any change in moisture content doesn't change the volume of our soil. In other situation, in higher moisture contents, if you dry your soil will lose some volume. But at that stage, the soil is very dry. There is no more volume loss due to water content change. So the boundary between my handwriting is horrible. The solid phase and semi-solid phase is called shrinkage limit. How about the boundary between semi-solid and plastic? Plastic limit. It's plastic limit. And the boundary between plastic and liquid limit is boundary between plastic phase and liquid phase is liquid. So those limits are basically just some moisture content that can transfer from the soil mass from one phase to another. We'll look at different soil classification systems. Now, just based on look at those symbols, what can you tell me? GW, what does it mean? GW, well-graded gravel. CL,
Low plasticity.
you shouldn't say. CL, I said that I still have it here. L stands for low plasticity. It means that you have a clay soil that has low plasticity. We call low plasticity clay lean clay. And if you have high plasticity, we call it fat clay. So low plasticity, we say lean. High plasticity, we say fat. How about MH? Silt. O. OL. I didn't mention O. O stands for organic soil. Organic soil, the only way that we can say if it's organic or not is you have to dry your soil and run liquid limit test. If you see a major change in your liquid limit after drying your soil, it's organic. It's basically from the name you can say if you have like roots or vegetables in your soil, and it's a sign of problem. You shouldn't build any type of structure on organic soil. If you have any organic soil, you have to remove that. And the only way that we can find out if it's organic or not is basically by running liquid limit test. Dry the soil sample around the liquid limit and see if there is a significant difference between liquid limit before drying and after drying. But we don't have dual symbols here, those borderlines. Remember that when we have fine content between 5 to 12%, we have borderline soils. For those borderlines, we have two symbols. The first symbol characterize the coarse grain part of our soil. For example, something like SW. This symbol has only, it has nothing to do with the fine grain soil. SW, well-graded sand, nothing related to plasticity. When you deal with dual symbol soil, the first symbol is just for the coarse grain, the second symbol is for the fine grain. So you will have something like, I don't know, for example, SWMH. It means that the coarse grain is well-graded sand, the fine grain is lean silt or low plastic. See. Okay. Weight volume relationship is very important, and for sure you will have at least one or two questions from weight volume relationship. First, any soil mass has three different phases. It's formed by three different phases, which are solid, water, and air. Now, in this basically, you know, that's funny. We're supposed to cover everything in soil mechanics and foundation in 2 hours. We have three phases, and what we want to do in this chapter, in this type of analysis, is to find weight and volume for different conditions. The first thing that you have to remember is Whenever you saw a problem related to weight or volume, definitely draw the phase diagram. That's the key. So, where is that? Draw phase diagram. And then show different weight and volume components on the left and right side of your phase diagram. We call air and water together voids. We have basically some solid particles. We have some voids between those solid particles. Those voids can be filled by water or air. So voids include water plus air. And in terms of volume, each of those components can have volume like volume of solid, volume of water, volume of air. Volume of water plus volume of air will be volume of void. But in terms of weight, of course, air doesn't have any weight. So total weight is just simply weight of solid plus weight of water. So the first thing that you need to do, draw a phase diagram. Second, find different volume and weight components. When I say different volume and weight components, let's start from one side, find weight, volume of solid, then find volume of void, then weight of solid, and then weight of water. If you can find those components, you can find anything that you want in terms of volume or void range. But you need to just remember some key definitions. Some key definitions that we have. We have three main volume relationships. Which are void ratio. When I say volume relationship, means you can calculate them based on just volume component. The second one is porosity. Third one is degree of saturation. We calculate void ratio. From the name you can say that void ratio is a ratio between volume of void divided by volume of solid. We use E to show void ratio. Porosity is similar to void ratio, but instead of dividing it by volume of solid, we divide volume of void divided by total volume, and we show that by N. How about the degree of saturation? Degree of saturation is we want to see how much of our void volume is filled by water. So what we have to do is basically find out volume of water divided by volume of void. We said that volume of void can be filled either by water or air. In this situation, and we show it by S, degree of saturation. So remember, we have three volume relationship and we have two weight relationship. Jody, what's the first one?
The weight relationship? Specific gravity?
No, not at all. Weight relationship, we have two main weight relationship. First is moisture content or water content. Or sometimes people say moisture content. It's basically you want to see weight of the ratio between weight of water divided by weight of solid. We usually use the omega. and it's in percentage, use percentage. So this is the first one. The second weight relationship is, which has something related. It's basically a combination of both. Is unit weight, which is weight divided by volume. We have, and we showed by gamma, but we have different gamma. Now, look at this phase diagram. If you can find those components of weight and volume, you can find any of those parameters. Remember, the trick in those weight-volume relationship is if you have just 3 parameters, you should be able to find anything that you want. And other than that, it's just playing with different set of equation. You may get different, set of equation, but you have to get to the same answer. Now, to find different volume and weight relationship, usually to make our life easier and can find parameters, we make an assumption. What was the assumption? Volume. Volume is total volume or volume of solid? Which one? Total volume. You can assume both. They're different. We assume volume of solid. This is an assumption. You can either assume total volume is equal to 1 or volume of solid. Or. This is or. We cannot assume both. In most cases, you see that, in most cases, I mean,